This is a circular motion problem involving, of course, centripetal acceleration as well as centripetal force. I show, to begin with, Newton's second law applied to the radial direction for any object moving in any sort of circular path. The R component of the total force, which is the sum of the separate R components of the individual forces, equals the mass times the radial component, the R component, of the acceleration. In every single case, A sub R, the radial acceleration, will be the centripetal acceleration, V squared over R. I show a circular path of radius is 0.50 meters. There's a ball at the end of a string whose length is the radius of the circle. The ball's mass is 2 kilograms and its tangential speed is 4 meters per second. Currently, this ball is at the bottom of the swing in this vertical plane. There are two forces acting on our ball. One is the pull by the string, the so-called tension. And in this case, it points from the ball to the center, toward the center of the circle. Consequently, that tension force lies along the positive radial direction, the positive R-axis. The other force is the weight force, the pull by earth on the ball. The weight of the object is m times g, 2 times 9.8, 19.6 newtons. The weight vector lies along the negative r-axis. So the radial component of the w vector is going to be a negative number, negative 19.6. Now let's apply Newton's second law to the radial direction, repeating it here. F sub r is the sum of all of the radial components. There's only two forces, two radial components, therefore. T sub r, the r component of t, plus the r component of w, equals m times the r component of the acceleration. Well, the r component of t is the full value of t because t lies entirely along the r-axis and it's on the positive side, so it's a positive t. But the weight vector, as I said, which lies entirely along the r-axis, points in the negative r direction. Consequently, its r component is a negative, whatever its length is, negative 19.6. It's equal to m times v squared over r. V squared over r, you will recall, I hope, is the expression you use to calculate the centripetal acceleration. So there's your mass, m, here and there, 2, and then the speed is 4, square it, divided by the radius, 0.50. Final result, the tension in the swing at the bottom of the path is 83.6 meters. I suggest you take a look at the similar problems in the text, or in advance of that, find the tension in the string without my help, with all the numbers are the same, except the ball is at the top of the vertical path. What then will be the tension? Do you expect the tension when the ball's at the top of the path to be greater than 83.6? The same as at, or less?